Hi, I'm Scott Sulprizio. I'm with United Engine and Machine Company. We've been producing pistons since 1922. This is the second part of a two-part series on eutectic alloys for pistons. The first part we went through the characteristics of a eutectic alloy. And let me kind of review those for you quickly. The first major characteristic is that the alloy melts at a lower temperature than either of the constituents added. And that is probably the most important characteristic of a eutectic alloy. But the second is that it solidifies like a pure element. And when we talk about pure elements, we realize that when they solidify at a constant temperature all the way across. A non-eutectic alloy, when it starts solidification, the temperature will fall off as it's solidifying. So the second condition is that we solidify like a pure element. The third condition is that the alloy is mixed in specific ratios. And those ratios are 12% silicon to 88% aluminum. That ratio is what we consider a eutectic alloy, especially aluminum and silicon. So again, we're talking about silicon, the addition of silicon, and there's reasons that silicon is used in aluminum alloys. And so let's cover a few of those reasons, and it'll give you an idea why we use it. So first off is more of a manufacturing condition, and it is that when we mix silicon with aluminum, it improves its castability. It improves its fluidity, and you get very, very nice castings out of a silicon alloy. The other characteristics that we're going to look at are thermal characteristics. And the first one is it lowers the thermal conductivity. It slows the transmission of heat through the aluminum. That is really the first major thermal property. The second one is as we add more silicon, it will start reducing the thermal expansion of the piston. So the more silicon, the more controlled expansion that we get. And the third characteristic, and this is one that everyone I'm sure you'd be interested in, is it improves wear. And again, these conditions are all relative to the amount of silicon that we add into the application. So again, in these three, lowers thermal conductivity, lower thermal expansion, and it improves wear. Let's talk about how a piston designer or someone might go about choosing a particular eutectic alloy for their application. So as we stated that at 12% silicon to aluminum, that this is the eutectic point for the metal. But in some cases we add more silicon and we add less silicon. And in those conditions, it puts things, I'm going to say, out of balance, that the alloy doesn't like having too much or too little silicon. So in the case of too much, we call this a hypereutectic alloy. It's above the eutectic point. So the way the alloy corrects itself is it starts forming pure particles of silicon throughout the whole casting. And as it's doing this, the silicon in the remaining liquid starts lowering. And it keeps forming these particles until the silicon in the liquid gets to 12%. When it gets to 12%, at that point, it solidifies. And again, it solidifies like a pure element, and it goes through our normal characteristics that we talk about for a eutectic alloy. So we're going to put up a little chart here to show you, it's called the phase equilibrium diagram. And in this chart, you'll see that as the temperature starts falling, how particles start forming, and when they hit 12%, you'll see that the material will solidify. So let's go the other way. We put too little silicon in, okay? And when we do this, again, the alloy is in an unstable state and it wants to correct itself. So in this case, we call this a hypoeutectic alloy under the eutectic point. And what happens is we start solidifying off pure aluminum particles through the whole piston. And that process keeps on going the same as for a hyper. And now the amount of silicon in the liquid starts rising as we crystallize off aluminum. When it gets to 12%, it solidifies, and again, we have our piston. So we have three conditions. We can have a piston at the eutectic point, we can have one over a hypereutectic, or we can have one under a hypoeutectic. So these characteristics will either improve the the thermal properties as we get more silicon in, or it'll lower it, but it'll improve its ductility. So when we buy these alloys, we buy them in two types. We buy a bar stock and we buy a ingot. And in the case of the ingots, that is almost used solely for casting. And in the case of the bar stock, it's used pretty much solely for forgings. But in both cases, they're eutectic alloys and they have eutectic characteristics. So I'm going to put up a little chart here that shows, as we go from left to right on this chart, how the characteristics will change as we move up towards hyperalloys. Now, in the case of hyperalloys, the silicon goes as high as 24%, maybe even higher. There's some heavy-duty alloys that are up in that range. The lowest one that we use, though, is 2618, and you'll see it on the far left of the chart. It is about 0.23% silicon. Now, this is a very interesting alloy, and the reason I find this is because there's some history to it. And the history is that it was developed for the Spitfire in World War II. A company out of England developed it, and it was used in those airplanes. When you look at your most common alloy that you use for performance, it's the 2618. As we move up this chart, you'll see we get to the eutectic point. We have a couple of alloys, 332, which is a casting alloy, about 9% silicon. And as we're doing this, those thermal properties are improving. But the thing I think you want to understand is that there's no alloy that has the characteristics of high ductility, very ductile, and thermal properties. It just doesn't exist. There's not the perfect alloy. But you have choices. So as we move up from 332, which is a cast alloy, about 9%, we get to 4032, which is a forging alloy, almost at the eutectic point, right at about 11 to 12%. Then we move into the hypereutectic alloys, 390, and then on up to 24%. So as you look at this chart, it'll give you an idea. Now, the reason this is important to you as an engine builder is you can pick these characteristics that you want to apply to your motor. If you feel thermal properties and low thermal expansion is more important, then you'll want to move towards the hyper side of the selection of alloys. If ductility is your characteristic, then without a doubt 2618, but then you lose these thermal properties, they just aren't as good. And so again, it becomes a choice that you have. So let me kind of wrap things up here and say, this gives you a little idea on how and what you might want to choose for a piston alloy. And I hope it gives you a little idea of, that it's not just a piston, there's more to it, and the alloys are a big part of that. So again, this is Scott Sulprizio. Thank you for listening, and we look forward to doing more videos for you, and I hope you enjoy this one.